Hello and welcome to our next lecture in CHY 113. Today we begin a new unit. In the first unit we focused in on looking at some of the tools that we're going to be using, some of the mathematical tools, and then looking at the structure of an atom. And now we start to shift to look at various aspects of chemical reactions. And so today and in the next lecture, we're going to focus on reactions themselves and look at the nature of reactions. And from there, we're going to go on and talk about some of the various aspects of the energy involving chemical reactions. And so let's go ahead and get going. Before we really do launch into it, though, one thing that we need to just bring up and talk about that I don't think I talked about or made clear when we were talking about molecules in general, is that there are some elements that exist as what we call diatomic molecules. That means that when these elements exist by themselves, they exist as one of the elements bound to another one. And so all of these different elements here, these 7 elements, so hydrogen, nitrogen, so on, when they're by themselves, when they are existing in their elemental state, you'll never find just one lone atom. They're always bound together. And so all of the oxygen that we breathe, for instance, all of the oxygen in the atmosphere, all of that exists as O2. And so there's always going to be one oxygen atom bound to another one. Now, again, keep in mind that that's only when these are in their elemental state, when they're by themselves. When they are matched up with other elements in different compounds, then they can absolutely exist in different ratios with different numbers. But when they are in their elemental form by themselves, they will always exist this way as diatomics. And so that's just something that we have to keep in mind, because the nature of chemical reactions, or what happens in a chemical reaction, is that atoms are combined in certain ways and in certain ratios initially. And through the course of the reaction, those compounds are going to come apart and then come together again, reconvene, so to speak, in different ratios on the other side of an equation. And so you might have, for instance, oxygen that's bound up with another atom in a compound, but then through the course of the reaction, it breaks up and it's by itself after the reaction takes place. So then when it's by itself, it would exist as O2. So again, this is just something that we have to keep in mind as we start to explore the nature of chemical reactions. And so a chemical reaction is displayed or is thought of in terms of a chemical equation. That's how we depict a chemical reaction, is by a chemical equation. So we can either have a word description of that equation. So for instance, in the reaction at the bottom, methane reacts with oxygen to yield carbon dioxide and water. And so that's just how we would say this reaction. It's how we would describe it and talk about it. The chemical equation gives us a symbolic representation of the reaction that occurs. And so we can see here the methane, our CH4, reacts with 2 different O2 molecules. And then through the course of the reaction, the methane and the O2s are going to bust apart, and everything's going to come back together to form 1 carbon dioxide and 2 water molecules. And so we would say that methane and oxygen react together to yield our CO2 and our H2O, or our reactants react to yield our products. Don't worry about these numbers in front, these coefficients. We're going to be talking about those. Those will make up a big part of our conversation today. But remember, these subscripts are just part of the chemical formula. And so CH4 is 1 carbon attached to 4 different hydrogen atoms and so forth. And so we do need to note that different terminology here in a chemical equation, remembering what our subscripts are, that they tell us the composition of our chemical formula, of our compound, versus the coefficient, which is the number of molecules that are going to come together and interact in an equation. So just a couple of vocab terms that we have to keep in mind going forward. Okay. And so chemical equations can also include other details. They can give us information about the states of matter that are involved in an equation. And so the equation that we were just looking at, methane, if we're looking at, especially at a room temperature equation, the methane is going to exist in the gas form. Our oxygen exists in the gas form. The carbon dioxide product will also be a gas, but the H2O liquid in this equation is going to be in the liquid form. And so we often see states of matter in parentheses after each compound in a chemical equation. Just provides us with some additional information. AQ, aqueous, means dissolved in water. And so we need to make a distinction between AQ and liquid. And so, remembering AQ means dissolved in water, versus L, meaning that it's the liquid form of a particular compound. And so we could have maybe a particular equation where we've got NaCl in its liquid form. That means that we're literally talking about taking some solid sodium chloride and melting it down until it becomes a liquid. That is going to be very, very, very different from NaCl aqueous, where it is now dissolved in water. And we'll take a look a little bit later at what that means, especially when an ionic compound is in an aqueous solution. But for now, we're just going to make sure that we understand that distinction between the two, that liquid does not mean the same as aqueous. Liquid is the actual liquid form of that compound. We've heated it up past the melting point. It's become a liquid, whereas aqueous means that we've just dissolved that substance in water. Chemical equations also show the relative amounts of things that are involved in a chemical reaction. It's like I mentioned before, those numbers are called coefficients, sometimes called stoichiometric coefficients. That's something else that'll make up a big part of this unit, is looking at the amounts in a chemical reaction. And that entire field or subject in general is known as stoichiometry. And so these coefficients are often called stoichiometric coefficients. And so in this example, we need 4 aluminum atoms to come together with 3 oxygen molecules, and that will form 2 units of aluminum oxide. Let's take a look at where those numbers come from. Ultimately, those numbers are a result of the law of conservation of matter. The law of conservation of matter tells us that atoms cannot be created or destroyed throughout a chemical reaction. And so whatever elements or whatever atoms that we have in the beginning, we have to have those in the end, and vice versa. Whatever atoms that we end up with at the end had to somehow be present in the beginning. Now let's take a look at what that might mean for us. And so in this example here, we're heating up some mercury oxide, so HGO. And so we're heating this up, and this is going to be a decomposition reaction. And so in a decomposition reaction, what happens is quite often we'll have a binary compound like this that's going to then split apart. And so we have our HGO, we have our mercury oxide. It's in its solid form. And it's going to then come apart. So the mercury is going to separate from the oxygen. So we're going to have our mercury. But now, one of the things that we have to remember, I'll just jump back to it real quick. We have to remember that oxygen is one of our diatomic molecules. And so whenever oxygen exists by itself, it's always going to exist as O2. And so that's very, very important for us here, because now that oxygen has to exist this way as O2. Sorry, bring it back to here. And so that oxygen has to now exist as O2. We run into a problem here, though, with the way the equation's written. Take a look and think about it. Think about what I just said as far as the law of conservation of matter. And think about what our issue might be right now. You see it? We have 1 oxygen atom here to start out. So our initial equation only has 1 oxygen in there. But here in our products, we have to have 2, because that's the way oxygen exists when it's by itself. So that violates the law of conservation of mass. We cannot have that situation. And so we end up putting our coefficients in front, and we'll talk about why we use coefficients in just a minute. But we're going to put our coefficients in front and say that we actually start with 2 mercury oxide units. That gets us our 2 oxygen atoms. Now we're starting with 2 oxygens. However, we're now starting also with 2 mercuries, but we only have 1 mercury over in our products. So what we have to do then is say that we're going to actually end up with 2 mercury atoms as well. What we've just done is known as balancing our chemical equation, one of the most basic and fundamental tools of chemistry, because it allows us to see the amounts involved in a chemical reaction that have to be present so that we don't violate the law of conservation of matter. Let's take a look at where those coefficients come from. So here's a nice simple example of the creation of water. This is something that really can be done pretty easily. Take a balloon full of hydrogen gas and oxygen gas, touch a little flame to it to kickstart the reaction. It's going to blow up because they're both fairly explosive, but it's going to blow up, and in doing so, you're going to get this little mist of water droplets that comes down. So we started the reaction, we're going to form water. But let's take a look at this. So we're starting with 2 hydrogens. Okay, we end with 2 hydrogens, so that's okay. We're starting with 2 oxygens, but our equation for water only has 1 oxygen. And so it's really tempting, and then we do a little count here, the oxygen atoms are not balanced. It's really tempting to just say, well, why don't I just add an oxygen like this? Why don't I just say that it's H2O2? Now I have the same number on both sides. That seems fair, right? No, 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 no. Cannot do that. That is a totally different molecule now. Water is H2O. That's the very definition of what water is. 1 oxygen atom and 2 hydrogen atoms. And the equation that we're working with, the process that we're describing with this chemical equation, is the formation of water. So it must be H2O. We cannot simply change our subscript because that changes the molecule in question. So we cannot simply add a 2. Incidentally, does anyone know what H2O2 is? Hydrogen peroxide. So again, a very different molecule. And so we cannot simply change the subscripts. What we can do is adjust the number of molecules that we have. That's what the coefficients do. And so in order to have 2 oxygens on our product side, in order to have 2 oxygens on the right side of our equation, we can do that by having 2 water molecules instead. So we're going to form 2 entire water molecules. Now we have 2 oxygens over in our product side. But we can see what this does for us. Now we have 4 hydrogen atoms in our product side and only have 2 in our reactant side. So we need to go back and fix our number of hydrogens. So we're going to say that we have 2 hydrogen atoms, or sorry, 2 hydrogen molecules. Now our equation is balanced. Let's take a look at this, actually writing the molecules out. So we're starting out with H2, so there's an H2, plus O2, so there's our O2, and that's going to form an H2O. And so this is the same exact thing, I'm just writing out the molecules in this structural format so that we can actually see the atoms involved and see their connections. And so again, we want to count the number of atoms that we have on each side. We have our 2 hydrogens over here, and we have 2 hydrogens over here. So we're okay that way. 2 oxygens here and only 1 oxygen here. So we know we need to fix our number of oxygens. So again, we know that we cannot simply add an oxygen like this. We can't simply add an oxygen onto this molecule. That doesn't work. It's not water anymore. So we're not going to do that. What we can do instead is say that we're going to form another whole entire water molecule. And so there it is. Now we formed 2 water molecules, and so we now have 1, 2 oxygen atoms. Perfect. But that means that we have to form 2, 3, 4 hydrogen atoms as well. We're only starting out with 2 over here on our product, or sorry, on our reactant side. And so that just means that we need to start with 2 hydrogen molecules. Remember, hydrogen is another of our diatomics, so it will always exist as H2 when it's by itself. And so now if we just count everything up, so if we look at our initial reaction, we had H2 plus H2O forms H2O. But we can see here, in order to balance our equation, we had to have 2 H2 molecules from up here. And we also formed 2 H2Os. And so that gives us our subscript in front of our water, 2H2O. And so I always like to provide this little visual representation too of what's going on in balancing, because I think looking at the actual equations like this, looking at the structures drawn out like that, really helps you to visualize what's going on and see that where we need extra atoms, and we can do that by having an entirely new molecule, or sorry, not an entirely new one, but an additional molecule form. And sometimes you need more than one. Or more than one extra, and we'll see some examples of some more complicated balancing a little later. And so here's another example. So here we have some NaCl plus mgbr. And we'll look more at reaction types at a later time. So NaCl plus mgbr is going to form NaBr and MgCl2. And so this is sort of a classic double displacement reaction. Actually, let's take a peek at this now. I want to show where this is coming from. And so we have our NaCl plus mgbr2. So let's just rewrite that over here. I want to show you where the actual products are coming from. And so this is what we would call a classic double displacement reaction. In a double displacement reaction, the positive and negative ions are going to change partners. And so our positive ion from sodium chloride is going to come together with our negative ion from sodium bromide. Sorry, okay. And vice versa. Our positive ion from magnesium bromide will come together with our negative. And so we're going to swap around. And so the easiest thing to do, I think, when you're first approaching these, is to identify the charge and the type of charge on each ion. So we know that sodium is a +1. We know that chlorine or chloride is a -1. We know from our periodic table that magnesium is a +2, and that bromide is a -1. And so our new combinations, Na is going to come together with Br. So we have a 1+ with a 1-. And so those are going to come together, remembering everything from the last unit, those come together as NaCl. So there's one of our products. We also have magnesium with its 2+ charge coming together with chloride with its 1-. Sorry. Hopefully somebody caught that I did the wrong thing. Let me just fix this one. That should have been bromine. I don't know why I did chloride there, so my apologies. We'll just take care of that real quick. NaBr. There. And so then our other product is the MgCl2 that we've also formed. This is why we end up having to balance equations, because things might exist in different ratios on one side of the equation compared to another. And they're going to exist in those different ratios because of the rules that we learned in the last unit about how ions are going to come together to form compounds. They're always going to come together in such a way that they'll end up forming a neutral compound. When sodium comes together with bromine, it's going to be in the formula NaBr. It doesn't need 2 bromines. It's not going to come together as NaBr2, because that's not the formula for sodium bromide. That's not the formula for when they come together. And so this 2 is not simply going to get carried over. This is a 2 in this formula because that's how magnesium and bromine come together. It's not how sodium and bromine come together. And so we end up with different subscripts, or we can end up with different subscripts from our reactant side over to our product side, which then leads us to having to balance the equation. So I wanted to show this to show where the balancing comes from. It's because we recombine elements from our reactants to our products, and in that recombination, they could very well be coming together in very different ratios than how they existed in the reactant side, which leads us to then having to balance our equation. And so we'll come back to this one, to how we balance it. And so we go through and we do our counting, and we see that we have a problem with our chlorides. We have, and our bromides for that matter. We have 2 bromines on the left, only 1 on the right, 1 chlorine on the left, and 2 on the right. So we have to fix that. Now again, we cannot simply do this. We cannot simply change the subscripts. We can't put a 2 in there for after the chlorine and after the Br, because that's not how sodium and chlorine come together. That's not how sodium and bromine come together. So you cannot simply change the subscripts. Our subscripts have to be dictated by the rules that we learned in the last unit. And so we can't simply do that. What we can do is change the number of NaCl's and the number of NaBrs that we have. Putting our 2's in front here as coefficients, that balances the equation for us. Now we have a correctly balanced equation. Let's look through a more complicated example. Oh, sorry, let's look at some of the rules. Once the equation is written, once you have the subscripts, those cannot be changed. And I can't emphasize that enough. The subscripts will not change once they are set. Subscripts are determined by the rules that we learned in the last unit. And we have to abide by those rules. To satisfy the law of conservation of mass, we'll use coefficients in front to balance our chemical equations. So here's our example of methane that we looked at earlier. So we go through and we can see that we need additional oxygens and we need additional hydrogens. We're going to look at our process here in a minute. But we can see that a 2 in front of our O2 and a 2 in front of our H2O, that now gives us a balanced equation. We have the same number of every type of element on both sides of our equation. That's your ultimate goal when you balance. The same number of each type of atom in your reactants and in your products. So we have various steps in writing a balanced chemical equation. We can write the equations using the formulas of the reactants and the products. We usually want to include our physical states. Balance the compound with the most elements in the formula first. So we'll see an example and we'll see what we mean by that. Any element that's on its own, save that for the last thing to do. So in this last equation, for instance, we would have wanted to maybe balance the hydrogens first, and then we could have taken care of our oxygens because oxygen was by itself here. I'm sorry for this little blurb that pops up. And then we want to check everything out and make sure that everything does, after we've balanced it, from there it's literal counting. If any of you come to some my virtual office hours and we work some of these, some balancing, you're going to hear me say something that sounds condescending but really isn't. You're going to hear me say count. Or you're going to ask me if an equation is balanced, and I'm going to say count. That's all it comes down to. Count your number of each type of atom on one side. Count your number of each type of atom on the other side. If those numbers are equal, it's balanced. If they're not equal, not balanced. And then if you can simplify it, if you end up with like 3's in front of everything or 6's in front of everything, then go ahead and simplify that down. Sometimes a trial and error approach works best. just sort of looking at, honestly, this is the approach that I usually take. I look at one thing that seems to be out of whack, and I fix that. I look to see if that changed something else for me, and do I have to fix that? And then I sort of keep going back and forth like that. The more of these that you do, the better you're going to get at some of these different approaches. So here's an example. So we have some calcium carbonate, decomposes to form calcium oxide and carbon dioxide gas. So we're going to start off by counting. We're going to see that we have 1 calcium in our reactant side, 1 in our product side. We have 1 carbon on each side. We have 3 oxygens on each side. And so it turns out that this equation is balanced as written. We don't have to do anything to it. We don't have to add any coefficients. It is already balanced. Here we have the combustion of some ethane. So C2H6 plus O2 react to yield CO2 and H2O. So again, we'll sort of go through it and do some accounting here. We have 2 carbons and 6 hydrogens and 2 oxygens in our reactant side. We only have 1 carbon, 2 oxygens, total of 3 oxygens, and 2 hydrogens in our product side. So we can already see that we're going to have to adjust some things. We're going to have to fix some things. And so the first thing that we maybe want to fix, or we want to save O for last because it's by itself. All right, oxygen is by itself right here, so we're going to save that one for last. And so the first thing that we might look at is maybe the hydrogen. We have 6 here and only 2 over here. So we're going to maybe look to fix that first. We have H2O in our product side. So the way that we can have 6 hydrogens is by having 3 total H2Os. Now we have 6 hydrogens. And so we can see now, though, that a sort of a problem that we've run into, and you'll see this sometime, especially with these combustion reactions, is that this side is always going to have an even number of oxygens, because it's O2, and that's the only place that oxygen appears. This side is now going to have an odd number of oxygens. Right? So we've got our O2 here, but now 3 H2Os. So there's nothing that we're going to, if we leave this 3 here, if we leave this odd number, there's nothing we're going to be able to do in order to fix our number of oxygens. If you run into that, then go ahead and just double what you've already done for the oxygen. Put a 6 here instead. That way it gives us even numbers to deal with because we know we're going to need even numbers over on this side. And so then we can go through and fix some other things. We can see that we're going to need 2 C2H6s because we now have 12 hydrogens here. This gives us 12 hydrogens over here. And this is just the same slide. We're just going forward. We're going to go ahead and fix carbon next. 2 C2H6s, so that's 4 carbons. So we're going to need 4 CO2s to balance that out. Now, finally, we can take care of our oxygens. We have 4 CO2s, so here's 8 oxygens here. We have 6 H2O, so that's an additional 6 oxygens. So we have a total of 14 oxygens over in our product side. So in order to get 14 oxygens in our reactant side, we need 7 O2s. Now we have a balanced equation. Count everything up. We have the same number of each type of atom on both sides of the equation. That's our ultimate goal. And so here's some practice. Go ahead and work through some of these. Sorry, that was the one that we just did. Sorry, just a different approach. So we're going to balance our biggest molecule first, our C2H6. So we're going to go ahead and put our 2 and our 3 here because that takes care of both our carbon and our hydrogen. Again, this is the same one that we just did. It's just sort of a different approach and a different way to look at it. We can see that our carbons are okay, our hydrogens are okay. We need to do something about our oxygens. Now, if you get to this point, and you might get to this point with just certain balancing reactions that you do, get to this point and you say, geez, if I could just put a 3.5 here, that would take care of it. And it would, right? We have our 7 oxygens over here. So if I could have 3.5 O2s, that would also give me 7 oxygens. And so if you reach that point, go ahead and put, in this example, the 3.5, go ahead and put that there to start out, just understanding that you are going to need to adjust that. We'll sort of keep it there as a placeholder for just a minute. And then we look through this and we see that, okay, now everything is balanced. We have the same number on each side, but we can't have a half a coefficient. We can't have a 3.5. And so if you get to this point where you're completely balanced, but you have a half coefficient, and like I said, that's okay as long as you recognize it's a step along the way. Get to that point and just double everything. Double everything in there. 2 of our C2H6s, 7 O2s, 4 CO2s, and 6 H2Os. So again, same exact equation as the last one we just did, just a different approach. Cannot stress this enough. We can only ever change the coefficients. I know that you've heard me say that a number of times. Even still, I guarantee some of you are going to try to change subscripts. Don't do it. We can only change our coefficients. So again, we'd be tempted to put a 2 there. We cannot do that. We put our 2 in front as a coefficient. 2 entire HGOs. And then we would have to have 2 HGs to start out. So go ahead and pause the video now. Practice these. Try to balance these equations. When you have them, go ahead and restart the video and check your answers. And I'll pause for a little bit. Okay, back. Hopefully you did really pause the video. I highly recommend you do so. If you didn't, if you cheated, pause the video now. Do these and then come back. And then hopefully this is what you came up with. Okay, to shift gears just a little bit now and talk about electrolytes versus non-electrolytes. We're going to talk about aqueous systems here. Because the reality is that many chemical equations are going to take place in water. They're going to take place in some sort of solution where we're going to dissolve our solutes and we're going to have a solution as a result of that. And then that gives us a venue, gives a medium for the reaction to take place in. And so we have to talk about what happens when something dissolves. And that's going to lead us to this idea of electrolytes and non-electrolytes. Electrolytes conduct electrical current. A strong electrolyte is something that's made up of 100% ions, or 100% of the molecules in there are in their ionic form. That's a better way to put it. All of the molecules in a strong electrolyte are in their ionic form. Weak electrolytes consist of more molecules than ions, and we'll see what that means in a few minutes. Non-electrolytes don't conduct current at all. And so they could still be a solution, still be a solute dissolved in a solvent, some sort of aqueous solution, but a non-electrolyte is not going to be a solution that conducts electricity. For instance, water is a non-electrolyte. Now I hear some of you thinking, well, geez, I know that water actually does conduct electricity though. You know, I don't want to be sitting in a lake when lightning zaps it. I'm going to be in trouble. And you're right. But that's not pure water. What's happening there is that there are absolutely electrolytes within the water. There are ions dissolved in the lake. That's what's passing the electricity through. If you have absolutely pure distilled water with nothing in it, you could stick your finger in that, have it zapped with lightning all day long, and you're going to be fine. And so pure water is a non-electrolyte. We'll look at this a little bit later, but there are some ions in pure water, but they're at concentrations too low to actually conduct electricity. So to figure out if something is an electrolyte or not, we can go through this flow chart. And so if we have something that's in an aqueous solution, anything in an aqueous solution, if it's an ionic compound, it's a metal and a non-metal, or a metal and a polyatomic ion, if it's anything that we've termed ionic from the last unit, that will absolutely be a strong electrolyte. If something is a molecular compound, then we have to think about it a little bit. Most molecular compounds are non-electrolytes. The majority of them are going to be non-electrolyte solutions. If we have acids and bases, however, though, a strong acid is going to be a strong electrolyte. And there are definitions of strong acids, which we'll get into. But anything that is a strong acid is a strong electrolyte. Anything that's a weak acid or a weak base, those are weak electrolytes. And we'll see what that difference is in a little bit. But so we'll go through this little flow chart to determine if something is an electrolyte or not. And so some things to be asking yourself, if we're wondering, is something an electrolyte? Is it molecular or ionic? You know, that's our first question. If it's ionic, it's a strong electrolyte. If it's molecular, then we have to think about, is it an acid or not? Or is it an acid or a weak base, perhaps? Is it going to conduct electricity? If it is an electrolyte, or in general, is it a strong, a weak, or non-electrolyte? And then how we symbolize that. So for instance, NaCl, ionic, right? It's one of our classic examples of an ionic compound. So we know that it is ionic, and so the solution itself is going to be a strong electrolyte. And we would represent that this way. And so that's the key. If something is an electrolyte, it's going to split up into its ions when it dissolves in water. And so what actually exists in an NaCl aqueous solution is not just NaCl still lumped together. It's the sodium ions and the chloride ions. That is the key defining aspect of an electrolyte solution. And so let's take a closer look at that. So we have NaCl as a solid, and then let's say we dissolve that in water. So then we have NaCl aqueous. What actually exists, what this really means, is that what exists in that aqueous solution are the sodium ions and the chloride ions. That's going to be very, very important for us going forward, is that recognition that that's what an ionic aqueous solution is. When we have a strong electrolyte, it means that all of the NaCl in there, every bit of this NaCl, is actually going to exist as the ions in that solution. And we'll see what that means for us in a little bit. Now we have table sugar, common table sugar, sucrose, C12H22O11. So we ask ourselves, ionic or molecular? That's all nonmetals, right? So it's going to be a molecular compound, a covalent compound, which means that this solution is a non-electrolyte. So this solution will not conduct electricity whatsoever. Since it is a non-electrolyte, this is going to be our best representation of it, is just the C12H22O11 all still together. That's not going to break up into its ions. There aren't any ions in here. It's molecular, it's covalent. And so we represent that by showing all the atoms still together. HCl. Now this is where we do need to just introduce strong acids and strong bases. Or sorry, just strong acids for now. The strong acids, that especially the ones that we're going to run into, we'll talk about some more later on, but HCl, HBr, HI, HNO3, nitric acid, phosphoric acid, and H2SO4. And when we talk acids and bases a little later in the class, we'll talk about some other defining aspects. But for now, you just need to know that these are strong acids that we're going to run into. And so we have to remember that strong acids are also going to be strong electrolytes. And so HCl, the solute, is molecular. So because we talked about H or talked about hydrogen being a non-metal, so we would say this is a molecular solution, but it is also going to be a strong electrolyte because HCl is a strong acid. So since it's a strong electrolyte, we represent it as breaking up into ions. NaOH, ionic, right? Because we have our sodium ion and our hydroxide ion. Yet another illustration of why it's important to memorize your polyatomic ions. OH is our hydroxide ion. So this is going to be a strong electrolyte, and we would represent it as the ions breaking apart in solution. Now, acetic acid, that's not on our list of our strong acids. So acetic acid is a weak acid. What this is going to mean is that when acetic acid dissolves, so we have our HC2H3O2. When acetic acid dissolves into water, some of it is going to absolutely just stay together. It's not going to come apart. It is just going to stay as is, just like sucrose did. Some of it, though, is going to break apart into H plus in the acetate ion. So again, polyatomic ion is our acetate. So some of it's going to stay together, some of it's going to split apart into its ions. That makes it a weak acid, and it makes it a weak electrolyte. So that's what we mean when we say some of the molecule will come apart. So just to make up, these are completely made up numbers. But for instance, if we had 100 acetic acid units, then maybe 95 of them stay completely together. But 5 of them come apart into their ions. Those are the worst 5s I've ever drawn. That makes me feel a little better. Okay. Now again, those are completely made up numbers, but it's just to illustrate that only some of these are actually going to break apart, but some of them do. Those of you who go on later to Chem 115, this will actually make looking at how much actually comes apart will make up a big part of what you study in that class. It's all in the subject of equilibrium and taking a look at how much will actually come apart. But for now, we just need to know that in a weak electrolyte or a weak acid situation, only some of those actually come apart. And so we can go through and we can see that it is conducting, but only weakly so. All right, I'm not going to worry too much about NH3. So again, you would just sort of go through this flow chart, and really the big takeaway, the thing that I really need you to take from this is that ionic substances are going to come apart in solution. And what exists in the aqueous form are the ions separated from each other. Whereas covalent or molecular compounds aren't going to do that unless it's an acid or a weak base situation. And then something might happen that way. But by and large, take away from this, ions or ionic compounds are going to come apart in solution. For the most part, molecular compounds are not. And so we're going to, our last subject for this lecture is to start looking at one of the driving forces behind a reaction. So when we're looking at a chemical reaction, one of the things that we need to ask ourselves is if we take these two reactants and place them together into a vessel of some sort, are they even going to react with each other? There's nothing to guarantee that a chemical reaction is going to take place. There has to be something that's going to drive that reaction to even occur. And so there are several driving forces behind a reaction. One of those is the formation of a precipitate, which is an insoluble solid, formation of a gas, formation possibly of a weak electrolyte can drive a reaction to happen. And so any of those three things, if those are outcomes of a reaction, or potential outcomes, then they could force a reaction, they could cause a reaction to actually occur. Let's take a look a bit at the first one for the rest of this lecture. So one of the things, in order to know if an insoluble solid is going to form, we need to be able to identify what compounds are soluble in water and what compounds aren't. For molecular compounds, we have to look at what we call the polarity. And that's something that will be the focus of our conversation, or the focus of one of our units a little bit later in the semester. For now, we're going to focus in on ionic compounds, and the solubility, if something is soluble in water or not, is governed by a set of solubility rules. So let's take a look at those. And so this is a list of all soluble compounds. These are things that absolutely will dissolve if we place them in water. So remember that salt is just our chemical definition of an ionic substance. And so all salts, all ionic substances that are made up of sodium, potassium, or nitrate, if they have, ammonium, if any of those are the positive ions, then the substance is soluble. Doesn't matter what else it's paired with. Doesn't matter what your negative ion is. If your positive ion is sodium, potassium, or ammonium, the substance will dissolve in water. It is soluble. Likewise, if your negative ion is nitrate, chlorate, perchlorate, or acetate, that substance will be soluble. Again, doesn't matter what the positive ion is. If your negative ion is any of these four, that is a soluble compound. Almost all salts of the larger halogens, chloride, bromide, and iodide, again, regardless of what the positive ion is, salts containing these ions will be soluble. Now we have some exceptions thrown in there, though. If our negative ion, if our anion is chloride, bromide, or iodide, and our positive ion, our cation, is silver, mercury with a 2+, or lead with a 2+, those are exceptions that are not soluble. And so in other words, silver chloride, not soluble. So even though most chlorides are soluble, silver chloride is not. Put silver chloride into water, it's just going to sit there as silver chloride. It is not going to dissolve. Put some lead iodide in water, not going to dissolve. It's just going to sit there. That's an exception to this rule. You can see that fluoride, most salts containing fluoride are soluble, but we have even more exceptions. And so magnesium, calcium, strontium, barium, or lead, those fluorides are not soluble. And then likewise, most sulfates are soluble, but we have these notable exceptions of calcium, strontium, barium, lead, and silver. Those would not be soluble. And so if just, like it says on the bottom here, if just one ion from the soluble compound list is present, then that compound is soluble in water, with the exception of the exceptions. Now we have our list of insoluble compounds. And so carbonates, phosphates, oxalates, chromates, and sulfides are all going to be insoluble compounds, except in the case of if our positive ion is ammonium or any of our alkali metals, where our alkali metals are our first column in the periodic table. So if we have any of these carbonates, phosphates, etc., but our positive ion is either ammonium or an alkali metal, then it is soluble. And so for instance, calcium carbonate, not soluble. Sodium carbonate, on the other hand, is soluble, and so on. Magnesium phosphate, not soluble. Lithium phosphate is soluble. And then also most metal hydroxides and oxides, not soluble, with the exception, again, of our alkali metal hydroxides. And so lithium hydroxide, sodium hydroxide, potassium hydroxide, and so on. and also barium and strontium hydroxide. Those would be soluble because those are exceptions to the rule. Okay, I thought I had some examples there, but I didn't. So let's come back to our list of soluble compounds. Just a little bit. And let's just look at a couple examples. So you can try to determine if something is soluble or not. And so let's look maybe at calcium nitrate. Soluble or not? Right, it is soluble. Hopefully some of you said that. So it is soluble because it's got nitrate in it. That means that it is soluble and there are no exceptions. Everything with nitrate in it is going to be soluble. Does not matter what your positive ions are. Magnesium nitrate, soluble. Lithium nitrate, soluble. Sodium nitrate, soluble. Doesn't matter. Every single nitrate is soluble. Every single compound that has sodium in the front, NaCl, NaBr, Na3PO4, sodium phosphate. Doesn't matter. If it has sodium in the front, it's soluble. If we start to look at some of our chlorides, bromides, and iodides, LiCl, soluble. Lithium's not on our exceptions. AgI, not soluble. So now we see that Ag is one of our exceptions. So that's how you use this solubility chart, is by first looking to see what category we're in. Are we in the soluble chart or the insoluble chart? You know, look to see where we're at, and then look to see if what you're dealing with is an exception to that in some way. And so in doing that, you can determine if a compound is soluble or not. You can use these solubility charts on your exam. And so I'll say that right from the get-go. You're going to use some of these enough, again, similar to your polyatomic ions and a bunch of other things. You're going to use these enough that you will have some of these rules memorized just from using it. But you do not have to know these by heart. I will allow the use of a solubility chart on your exam. And so for exam 2, which we'll need to start thinking about soon, believe it or not, even though you just took exam 1, for exam 2, what I'll do is I'll actually end up sending you out a sheet of information that you can use, that you can then print off and just have that in front of you. And the solubility rules will be on that sheet. So you'll be able to use these on the test. So that'll be it for now. When we come back for the next lecture, we're going to look at a big way of how we're going to use these solubility rules. I'll give you a hint just to sort of start us out and then show you just really quick, but then we'll get into some more detail next time. If we have an equation, for instance, let's say we have some sodium phosphate. I just want to check something real quick, sorry. Okay. So we have sodium phosphate plus calcium chloride. And these are both aqueous solutions. And somebody should have caught me. Hopefully you did. It's going to be CaCl2. Just forgot to write that in there. So sodium phosphate plus calcium chloride. Now we need to look at what our products are going to be from this reaction. So remember I said that the easiest way to look at the products is to first identify what the charges are on everything. So our charge on sodium is 1+. Phosphate, PO4, is our polyatomic ion with a charge of 3-. Calcium, a charge of 2+. Chloride, a charge of 1-. So we know that one of our new combinations is going to be Na and Cl. And so those are going to come together as NaCl. Our other combination, our other plus minus, is Ca2+. and our phosphate with its 3 minus. So those come together as Ca3 PO4 just from our rules that we used last time. So we've got Ca3 PO4 Now we can do one of a couple things. We could balance the equation at this point. Let's go ahead and do that. So we can see that we're going to need, we have 3 NAs over here, only 1 over here. So let's go ahead and take care of that first. Put our 3 in front. That's going to give us 3 CLs, and we've only got 2 over here. So wow, we can see that we've got a problem now, right? So this is one of the same problem that we ran into last time. So there's no way that we can sort of reconcile this even number here and this, or sorry, this odd number of CLs here and this even number here. So if we run into that, one of the easiest things to do, instead of putting a 3 here, we're going to go ahead and just put a 6. And we can see what that does to our CLs. Now as we have 6 CLs, so we can go ahead and put a 3 here to adjust for that. That gives us 3 calciums, and so that's good. We have 3 calciums over here. We have 2 PO4s over here, though, and we have 6 NAs. So we can see the way that we're going to fix that is a 2 in front of here. So now the equation is balanced, but now we need to also figure out our state of matter. We need to figure out our states for our NaCl and our Ca3PO4. So let's look at our solubility chart. We can see that, again, nearly all salts that have Na and pretty much all salts that have a Cl minus are going to be soluble. Na is not one of those exceptions. And so NaCl is soluble. NaCl is going to be aqueous. Ca3PO4, calcium phosphate. We don't have any rules for calcium or phosphates here on our soluble charts. Let's look at our insoluble list. Phosphates, most of those are insoluble. There are some exceptions, ammonium and our alkali metals. Calcium's not an alkali metal. Calcium's an alkaline earth metal. And so calcium is not an exception when it comes to our phosphates, which means that calcium phosphate is going to be a solid. And so if we were to rewrite this whole thing just a little bit neater, let me just see if I can erase all this down here. Maybe not. Oh, it's not letting me erase. That's okay. I'll just rewrite it down below. So to just rewrite this whole thing again, just so we're a little bit neater. So there's our fully balanced equation for our reaction between sodium phosphate and calcium chloride. And so we'll be working with, this is where we'll pick up in the next lecture and look at how we even analyze this equation down a little bit further. And so that's it for today. I will see everyone next time when we begin looking at ionic equations in even more detail. I hope everyone has a great day.